Good evening, students. In yesterday's class, I discussed mechanical equilibrium and chemical equilibrium. And in today's class, where I am going to discuss about thermodynamic criteria for two-phase equilibrium. Thermodynamic criteria for two-phase thermodynamic criteria for two-phase equilibrium for one component system. For one component system. Thermodynamic criteria for two-phase equilibrium for one component system. The component is one and phases of each is to 2. In this, consider a one component C is equals to one component system existing in two phases in equilibrium. Here, I write consider one component system existing in two phase in equilibrium. You consider one system. In that system, the component is one and two phases in equilibrium. Here, in two phases means I take H2O example. H2O solid vertical reaction H2O liquid. This is the one phase. And another reaction is here two phases. This one is solid, one is a liquid. The component is one. Water is here also water, here also water. And another H2O liquid vertical reaction H2O gas. Or it is written in this here, when some amount of the substance is transferred from one phase to another. Here, the component. Here, some substance is transferred to any some of the substance 1 gram or 1 is 0.1 gram, or here the one there is some amount of substance transferred from one phase to another, while the molar free energy decreases while other increases. Sometimes here the some amount of substances is transferred from one phase to another phase. When transferring one phase to another phase, so here phases increases while another decreases. One phase is increases and another phase is decreases. Here the net here decreasing and increasing the amount is here transformation is the amount of transformation is equal. And here hence the no net change in free energy. No net change in free energy, that is delta is equals to no net change in free energy. dg is equals to G2 minus G1. Here no net change, here dc is equals to 0. Here 0 is equals to G2 minus G1. Therefore, here G1 is on this side, here G1 is equals to G2. This is a expression for this thermodynamic criteria for two-phase equilibrium for one component system. Here G1 is the molar free energy of phase 1. Right here. G1 molar free energy for phase molar free energy for phase first. G2 is the molar free energy for phase 2. Here the conclusion is G1 is equals to G2. Here molar free energy for phase 1 and molar free energy of phase 2. These two are completely here equals. Here it is given in a given temperature and pressure, two phases of a single component are in equilibrium with each other. The molar free energy is same for each phase. The two phases, the molar free energy is same for each phase. Any given phase means here two phases are used. This is a two-phase system with one component. Okay, next heading, the Gibbs phase rule. The Gibbs phase rule. Gibbs phase rule. It gives gives phase rule. You know already gives phase rule, that is f is equals to c minus p plus 2. This is here. F is the degree of freedom, c is the number of component, and p is the number of phases, and plus 2 is the variables number of phases. Only two, one is temperature and another is the pressure. Here you derive this, how to derive this phase rule equation. First we have to consider the number of components and number of phases and transformation of one phase to another phase in a component. In one component or two component or three any component, here only syllabus one component and two component system. We gives phase rule is here we have to derive gives phase rule f is equals to c minus p plus 2. Here consider a heterogeneous system. I already told about this phase rule equation. Phase rule is the important to dealing with the study of heterogeneous behavioral heterogeneous system. Here we have to consider a heterogeneous system having p phases. First, consider heterogeneous system having p phases, that is here p1 p1 p2 p3 etc. p1 p2 p3 etc. pn and components are c1 c2 c3 etc. cx. And here I taken a system. The f is the total number of variables. Total number of variables. I taken this system. Here and C. Here C2, 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 C3, 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 C4, C4, C5, C5, component, these are the components, C5. Here, etc., etc., you take CX. Here, CX. these are the phases. Here phase 1, this is phase 2, this is phase 3, and P1, P2, P3, and C1, 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 and here P1, P2, P3, this is a P4, etc. Here is a Pn. These are the phases, these are the components. Here the variables here you will taken that is the temperature and pressure. Here the transformation of component in a one phase to another phase. Here, take an example. Here, the temperature and pressure are variables. It can be calculated from this phase-rule equation. First, temperature. The temperature at equilibrium here. In temperature at equilibrium, phases and component. The temperature in equilibrium phase, all the phases temperature are same. Here at equilibrium, each phase has the same temperature. So one variable is temperature. For whole system, this whole system, the temperature is same. This and temperature is one variable. This is one variable. Pressure is another variable. You written F is equals to C minus P plus 2. This is the phase rule equation here. This plus 2 here. This is the temperature and one is the variable. And pressure, the pressure in the system is in equilibrium. The pressure is also same in all the phases. Here at equilibrium, each phase has same pressure and composition. First one is the temperature. Second one is the pressure. Third one is composition. Here you take A and B components. Suppose A and B two components. Here C1, C2, C3, C4. And you consider A and B two components in a single phase. Here the molar free energy, a molar concentration of A is known. You take two components, this one and this one. A and B, and molar concentration of A is known. You know, molar concentration of A is known, and find out the molar concentration of here. B is finding here. B is finding here the molar concentration of this. Difference is obtained here with molar concentration of known and molar concentration of unknown. B components are different. One is obtained. It's a single phase having two components can be defined by one concentration term. Single phase two component system, it is defined by one concentration term. One concentration term. Here pressure is one variable, temperature is another variable. In composition, having the two components, considering the two components A and B, you suppose you take A and B components and phases, considering one single phase system. The another second component, the concentration term is different for one phase system is here. The concentration changes here. Concentration changes here. C concentration, P is the phases. Here this is the concentration in this. It is known as a component term is changes. Here component term is changes. Here a single phase containing C components. When right here. this diagram, which shows only the transformation of component from one phase to another phase. What happens? The pressure and temperature. In this phase, Gibbs phase. A single phase containing a single phase containing detect it. A single phase containing C components can be defined by C minus 1 concentration term. Here, the C minus single phase containing C components. Here, the single in above is C. Here, single phase containing two components. Here, single phase containing C components can be defined by C minus 1 concentration. Each phase has C minus 1 composition variables. These phases has C minus 1 composition here. And the total number of variables here, you know already, temperature is one variable and pressure is another variable. The concentration term is C minus 1. The total variables here, total variables is equals to the concentration term for single phase, one phase, C minus 1. Here, P is a single phase and concentration term, the composition of each phase is C minus 1. C minus 1. And plus 1. This temperature plus 1. This pressure. This is a temperature and this is a pressure. And here these are the concentration terms, that is a for composition. For composition for each phase. Composition for each phase. And here the equation is comes P C minus 1 C minus 1 plus the total number of variables here P is variables is equals to P into C minus 1 plus 2. Here one is the temperature variable and another is the pressure variable. This is the each concentration term in a single phase. The concentration term written for composition in each, that is single phase system, that is the P into C minus 1. C minus 1 is a difference concentration terms here. And here the number of relationship between the variables at equilibrium. These two variables are relationship between in equilibrium. What is the relationship between in equilibrium? First here, according to thermodynamics, you already studied this mu. It is a representation of in a mechanical equilibrium. Here, according to thermodynamics, mu of a component is same in all the phases. Mu of a component is same in all the phases. Then the system is in equilibrium. Then this is a two component. Here one, and next you consider a system having its three phases. One here I components and system having three phases. You consider a system is A, B, C. These are the phases. The system having three phases at ith components. Ith components. Here ith components. The system containing components and that go the phases. Here we have written variable is written as this is mu is written as mu IA is equals to mu IB is equals to mu I C. This is in yesterday class study this equation. Mu IA is equals to mu IB is equals to mu IC. And next, this is form two equation. This equation forms two equation. One is a mu I A is equals to mu I B, and another mu I A is equals to mu I C. These are two equations are formed from this equation. Next, to remember this equation, that is the number of variables is equals to p into c minus 1 plus 1 plus 1. This is a very important equation. And then here I consider that is the ith component and p phases, the number of phases A, B, C. And here if three phases, the presence of three phases, two equations are known. Here two equations are known for each component. And if p phases, C in component C concentration term is C minus 1. In p phases, the phases are written, there is a p minus 1. You write if p phases, if p phases if p phases p minus 1 equation for each component, p minus 1 equation for each component. Here p minus 1, here c minus 1, here p minus 1, here p phases is consider equation p minus 1 for each component. Hence, the for C components, hence for C components, relationship will be P into C into P minus 1. Here P into C minus 1 in phases, in components C into P minus 1 in components. And write the overall equation, that is phase rule equation here. Therefore, F is equals to variable. F is equals to this one, P into C minus 1 plus 2. We write this is a P into C minus 1 plus 2. This 1 plus 1 plus 2 minus of this one. That is a P C into, this one C into P minus 1. Simplify this equation. P into C, PC minus P plus 2. And here minus CP, or you can write PC minus plus C into 1 C. Here plus PC and minus PC get cancelled, and here right plus C minus P plus 2. Here F is equals to C minus P plus 2. Here F is the degree of freedom, C is the number of components, P is the number of phases, and plus 2 is the variable, that is the temperature and pressure. This is the derivation for Gibbs phase rule equation. It is very important for we ask for a right hand phase rule equation or a right hand expression for phase rule Gibbs phase rule equation. It is a physicals to C minus P plus 2 into 1 mass question important for 1 mass or 2 mass asks derivation of phase Gibbs phase rule equation. Next, phase diagram. Phase diagram. Phase diagram, or it is also known as PT graph or PT diagram or CT diagram. Here, phase diagram is plotting a graph. This is a temperature pressure. Here, temperature pressure versus this is a PT graph. And here, phase diagram is which shows the conditions of effect of temperature and pressure in a physical state. It undergoes the physical state for coexist in equilibrium, that is known as a phase diagram. For it taken the number of phases which can exist at equilibrium at any time depends on the conditions of temperature and pressure. It changes the only depends on the conditions of temperature and pressure or conditions of temperature and concentration. Here also taken temperature and concentration. Now temperature concentration taken temperature and concentration, this is it indicate TC diagram, or it taken P pressure and temperature, this indicate the PT graph. Here T and C at constant pressure. If taken temperature and concentration and pressure is constant. If taken temperature, pressure, concentration constant here, and these conditions of pressure and temperature are determined here experimentally and plotted PT graph and TC diagram. Here the diagrams contains the number of lines, areas and triple point. Here the number of areas, number of curves and triple points. This is known as areas, and this only one line is known as curve, lines or curves, and this is known as a triple point. This is a triple point, and here the phase diagram is defined as be showing that conditions for pressure and temperature under which two or more physical states can exist in equilibrium. This is known as phase diagram. Phase diagram shows the conditions of temperature, and pressure. Temperature and pressure under which two or more under which two or more physical states, two or more physical states exist in equilibrium. This is known as a phase diagram. And next, application of one component system. Application of one component system. One component system. In this one component system, only there are two applications. Here one is water system and another is sulfur system. In your syllabus, only water system and sulfur system. These two are very important for 5 to 6 marks. Water system is a one component system because here the phases are different. Here 2, 3 phases. You consider H2O solid and H2O liquid and H2O gases. Their phases are 3. Component is 1. This is a one component system. These are the application for the one component system. Then one is the water system, another is the sulfur system. These two are very important for 5 marks, and I explain water system tomorrow. I stop here. Thank you.